So today the goal is to obtain a Fourier cosine series using formulas that we just derived last time. And then we'll talk about some more aspects on how we denote these series, and there will be a need of practice with notations. It's going to be a little bit tedious in the beginning, but if you practice enough, it should be easier as we move along. In particular, it's important to make sure you understand the algebra, because the problems may give you the answer, or some types of series may appear in a format in the table a little bit different than your own, although it's going to be the same. So in order to make sure that your answer is correct, you may need to do some algebra manipulation to make sure before you conclude that you made a mistake, because you could be correct, but it's just a matter of simplification. So for now, let's focus on using those formulas. So let's remember what we did last time. We said that a function, a piecewise defined function on the interval 0 pi has the following, or let's assume it has the following cosine series representation. Okay, we assume it has this, right? No, this representation. And if that's the case, then the formula for the coefficients, so given a function that has a cosine series representation, the coefficients will be given by an equals 2 over pi, the integral from 0 to pi, f of x cosine of nx, when n is 0, 1, 2, 3, and so on. Remember, there's no need to take a formula separately for a naught, and that's the reason we have this extra 2. If we had just a naught outside the summation, we would need a slightly different formula for a naught, but as such is the same formula for all coefficients from 0 to infinity, 0, 1, 2, 3, and so on. So in practice, we won't do this with by hand, but using the tables, but let's actually do it for a couple of basic functions. So we're going to obtain, as an example, the Fourier cosine series for the function f of x equal to x on the interval 0 pi. Now you will see that in the process of computing that integral, you will still have to compute that a naught separately, because of the fact that you can divide by 0, remember? So that's always the case. I mean, you can anticipate that at some point you'll have to divide by n, right, if you integrate cosine of nx. So let's do the first one. Let's do a naught. So a naught is going to be 2 over pi, the integral from 0 to pi, x times cosine of 0 times x. So that's going to be the easiest one. Cosine of 0 is 1. The integral is x squared over 2. And between 0 and pi, 2 cancels. So you have pi squared over pi minus 0. That's equal to pi. So that's a naught. To compute an, we're going to use integration by parts. I'm going to actually write down, I like here to do an integration by parts formula a little bit different than the standard one taught in Calculus 2. So if you integrate from a to b, f times g prime, that's f times g between a and b minus the integral of f prime g. So I don't like to use the u and dv notation. You could do that if you want, but that's a little bit faster. So you just write your integrand, I mean your function to integrate in terms of a product between a function and its derivative, in such a way that when you switch the derivative, your integral becomes easier. So you need that because in this case, when you compute an, so an is 2 over pi, where n is from 1, 2, 3, and so on. So 2 over pi, the integral from 0 to pi of x cosine of nx. The obvious way to deal with this is integration by parts. You want to get rid of x via differentiation. So that means you need to write cosine of nx as a derivative. And we can do that by writing it as the derivative of sine of nx over n. And now, used by parts, x sine of nx over n between 0 and pi minus the integral from 0 to pi of x prime sine of nx over n dx. So let's not forget the 2 over pi in front of everything. So pi sine of n pi over n minus sine of x 0 times sine of 0, which is 0. X prime is 1. Let's do one more step here just to make it clear. Sine of n pi is 0. So here we have minus 1 over n. And the integral of sine is going to be minus cosine of nx over another n between 0 and pi. So you have to be careful when you deal with these simplifications here, because these minus signs and the 1 over n's popping up, and in general you'll have constants that depend on n that you'll have to deal with. So when everything is said and done, this will be 2 over n squared pi cosine of nx between 0 and pi. 2 over n squared, well, we can write pi n squared depending on your preference, cosine of n pi minus cosine of 0, which is 1. So that's one of the drawbacks of this method using series representations. You should expect tedious terms. That's the nature of the beast, so to speak. That's not to say we're going to focus too much on simplification, but you have to be patient and go slow. I mean, you basically, that's what you will see in the homework. Not too many problems, but many of them are a little bit longer, and you just have to basically be determined to go slow, step by step, and not rush. And I will say a little bit more on how you write these coefficients here. You can leave the coefficient like that, but for practical matters, you'll see this type of coefficient in various formats. But let's just write down the final answer before we talk about other versions of the way to write it down. So we determine a naught over here, that's equal to pi. This is a n. So what we concluded is that x can be written in form of a Fourier cosine series as a naught over 2. Remember, you divide by 2, a naught. So if a naught was pi, then the first term is pi over 2, plus the summation from 1 to infinity, a n, which was 2 over pi n squared, parenthesis cosine of n pi minus 1, and then times cosine of nx. So this is the cosine series representation for x, for the function f of x equal to x on the interval 0 pi. And as I said, you'll see various formats of this notation here. So for ones, typically it's customary to pull out the constant from the summation. And cosine of n pi cycles through 1 and minus 1. So again, going back to the unit circle, even numbers, even n's will give you 1, odd n's will give you minus 1, right? So cosine of 0 is 1, cosine of pi will be minus 1, cosine of 2 pi will be 1 again, and so on. So you will see in many books when something cycles through 1 and minus 1, that you can write that term either minus 1 to the n or minus 1 to the n plus 1, depending on whether it is 1 minus 1, 1 minus 1, or minus 1, 1, minus 1, 1. You just have to basically plug in the first value of n and make sure that you get basically the terms that you need there. It's nothing wrong to leave it like cosine of n pi. I don't really care one way or another that much, but you will have these different forms in various Fourier tables. So then you have to expect them and deal with them if they arise. So 2 over pi can be pulled outside the summation, and you're left inside the summation with minus 1 to the n minus 1 over n squared cosine of nx. So that's another format. And on the second page, I'm going to show you yet a different format that you will see in the table, which sometimes is more like a liability than a benefit. But again, you need to be aware of it and deal with it so that you can recognize it correctly. Because your answer can be correct, but you may not realize it's the same as the one in the book if you're not aware of this algebra. So stay tuned for the second part. All right, so here's another format of this series, which I actually kind of dislike myself, but it's, like I said, it's given in various tables, including the one you're going to use, the one given in the back of the book. And because sometimes it's more like a liability, like I said, than a benefit, but I'll have to write it down so that you're aware of it, like I said. So when you have, in this case, if you look here carefully in this series, we have minus 1 to the n minus 1. So if n is equal to 0, that's actually 0, right? Because that's 1 minus 1. If n is equal to 1, that's going to be minus 2. If n is equal to 2, that's again 0 because it's 1 minus 1. So actually, all the terms when n is equal to 0, when n is even, so if n is even, inside the sum is 0, right? If n is even. And if n is odd, the inside of the sum is going to be minus 2. So you could decide if you want to only write down the odd terms. Now, how do you write all the odd terms? 1, 3, 5, 7, and so on. Well, instead of saying n from 1 to infinity, you could, well, I mean, you can still write n from 1 to infinity, but instead of n, you're going to replace n with 2n minus 1. So that forces basically the coefficient to cycle through, I mean, to go through the odd numbers only. So n is still going from 0, 1, 2, 3, 4, and so on. But if you put 2n minus 1 instead of n, then you're going to end up with 1, 3, 5, so on and so forth. So yet another version of this series is to write minus 2 on the top, but instead of n, like I said, you write 2n minus 1. Instead of n, instead of like for cosine of x, you write cosine of 2n minus 1x. And to make matters even more confusing, one can also pull this minus 2 outside of the summation now. And if you look at the back of the book, I think this is the format you will see. Let me double check. This is the format you will see for, yeah, for the Fourier cosine series for x. Now, the reason that I don't really like it that much, although you could argue that it's more compact than before, is because we use tables of series to obtain series for other functions. So let me give you an example. On the back on that table, which at some point you will print it out, you will see, for example, the Fourier cosine series for x squared. Let's say the interval 0 pi like before. Okay, so x squared is gonna be pi squared over 2, pi squared over 3 plus 4 summation from 1 to infinity minus 1 to the n over n squared cosine of nx. So that's the series cosine series representation for x squared, and given in the table. And let's say that I want the series representation for let's see, for x squared minus x, or let's say 2x squared minus x as a cosine series. That's the whole point of using the table, in the sense that you could combine the functions. If you have basically a linear combination of functions in the table, you can combine them to obtain a cosine series without going through the formulas. But in this case, you know, if you have a Fourier cosine series given like that from 1 to infinity and n inside the summation for x squared, and then if x is given in this last format here, that's not going to be easy to combine these two summation into one summation, because that's what you have to put here, right? I mean, if you want this cosine series from the table, you're going to multiply by 2 the series for x squared, and then you subtract the series for x. But you better have those two summations going through the same values of n, basically, not just through the odds or evens, right? Like it happened for x. So for example, here I would rather prefer this format for x, for the series in the corner, because then I can combine the summations easily, as I can show you right now. So you multiply by 2 the series for x squared. So I'm going to throw it in here. And then minus x minus the series for x. And it's just a matter of combining the summations, right? So let's combine the constant term, I mean the term outside the summation. So we have 2 pi squared over 3 minus pi over 2. Then we have 8, let's see, let's do it one more step. So 8, 2 times 4 is 8. We're going to combine them on the next step. And then minus 2 over pi and then we can combine these two summations together. Eight minus 1 to the n over n squared, and then minus 2 over pi minus 1 to the n minus 1 over n squared cosine of nx. So at this point, if you're worried already about these tedious computations, don't be worried too much, because it's not important at this stage to actually spend too much extra time beyond what I just wrote right now to simplify. So for example, if this is your answer to the question in a problem, well, technically you can think about, for instance, simplifying, let's say, this parentheses if it's possible. If it's not an obvious way to simplify, just leave it like that. You can even compute the coefficients separately and leave it, not even plugging it back in the summation. So once you have the coefficients, once you find these coefficients, sometimes we can consider the problem as being done. So one last remark before we call it a day, and we're going to talk about this more later on. These series representations can be extended beyond the interval 0 pi because of the nature of the function cosine and sine, as you'll see later. And so let me end with this remark, but we will talk about this in more detail in the next lecture, but stay tuned for a short last part. Okay, so in this last part, I want to show you something that will be discussed a little bit more in later on, but for now, I want to introduce this concept of a periodic even extension. It's another way of saying that the Fourier cosine series, it's not good just for the interval 0 and pi. So you can extend the same representation for a larger interval. So the same Fourier cosine representation on the interval 0 pi that we started with can be extended, let me write it here, can be extended to a larger function. So this is because because it's periodic and even. That's the key thing. That's the reason why you can extend it this way. So let me remind you that if you even in this context means that if you replace x with minus x, you get the same value. So more generally, if you replace x with minus x in cosine of minus nx, you get the same cosine of nx. So you get the same values of f of x equal to x, right? So if you remember the previous example, so the same values of f of x equals x if we replace x with minus x. So because I mean the cosine representation, right? Because x was given in terms of pi over 2 plus 2 over pi, the summation from 1 to infinity, minus 1 to the n minus 1 over n squared cosine of nx. So if you look at the graph, let's just say this is 0 pi, this is the starting point, f of x equals x between 0 and pi. We get the same values in this series if we replace x with minus x. So that means the graph is flipped to the left side over the y-axis. And because cosine is periodic with period 2 pi, so the length of the interval is 2 pi, then the same shape can be repeated to the left and to the right. And again, it will have the same Fourier representation. So this will be 3 pi over here, 2 pi, minus 2 pi, minus 3 pi, and so on and so forth. So we can extend these representations to a larger function called, in this case, the periodic even extension. So what you see here, this seesaw basically, is the periodic even extension for f of x equals x with x between 0 and pi. So the starting point is between 0 and pi. That's the convenient starting point to compute those Fourier coefficients. But once you establish that series, again, the same series here can be extended to the entire function obtained via this periodic even extension. So this can be extended, of course, to any cosine series. So imagine you start with a function on the interval 0 pi, and let's say that function has I don't know, this shape like that, for instance. Can be any shape as long as it's piecewise continuous. So you start with a function between 0 and pi, you obtain its Fourier cosine series, whatever that may be. Then the same series will cover not just the function over the interval 0 pi, but it will cover the even extension, which means the original shape flipped over the y-axis to make it an even function, basically, and then extend the period to the right and to the left. So extend the shape over the intervals. So the start minus pi, and then pi 3 pi, and so on and so forth. We'll deal with that a little bit in more details later. There will be a similar statement for sine series. The sine function is an odd function. And then we're going to finalize the chapter later with generic Fourier series. Because as it turns out, you will see that functions which are neither odd nor even can actually be written in terms of a summation of an odd and an even function, which means that we basically combine these pieces together into what we call a general Fourier series, not just cosine and sine. So I think that's enough for today. We'll continue with probably more examples in the next lecture before we move on to sine series. So that's it for today.